Welcome to week 8 of Math 320. The end is in sight and we are ready to tackle functions. In the previous several weeks, you have practiced how to form epsilon n arguments for proving or disproving the convergence of sequences of numbers. In this week, the emphasis is to modify your thinking to apply the exact same techniques for discussing the limit of real-valued functions. Most of the functions we will be dealing with in this course are functions defined on an interval of the real line. So we will start by talking about limits of functions whose arguments belong to an interval. There are two main cases. The first case is when the interval is unbounded. The second case is when the interval is bounded. In the first lecture now, we will treat the unbounded case because the definitions there are almost verbatim copies of what you would do for infinite sequences. In the next lecture, we will discuss what happens when the interval is bounded. Specifically, we will discuss how to reformulate the epsilon n arguments of sequences into epsilon delta arguments for real-valued intervals. The third lecture, we will go through some basic theorems about properties of function limits. These closely mirror what we did for sequences, and we will go through them at a fast pace, mainly to use them to illustrate the change from the epsilon n idea to the epsilon delta idea. The final lecture, we will finally move on to study continuous functions. As you may remember from your calculus or college algebra course, a continuous function was defined in terms of having the limits from below and from above agree both with the value of the function at point being considered. We will reformulate this in an epsilon delta notation that is more flexible and allows us to treat functions whose domains are not necessarily intervals. Properties of continuous functions will be presented next week. The order of presentation I will make are opposite of what Ross is using in his textbook. So, the first 3 lectures from this week, we will jump ahead to material on page 153 through 162 of your textbook. While for the final lecture, I will return to earlier material about continuity of functions. Let's begin. We jump right into the definitions. Given a function defined on the real line, we say that f converges to L at positive infinity if for every epsilon positive there exists a real number capital X such that for every small x that is closer to positive infinity than capital X, the difference of f of x and L is less than epsilon. Yes, I just described the membership of small x in the interval from capital X to infinity as small x being closer to positive infinity than capital X. This is a useful way of thinking about the ordering relationship and will be helpful later. When we take limits, we should be thinking about numbers getting closer and closer to a point. Even though infinity is not strictly defined, we can have an intuitive notion of what it means for a number to be closer to positive infinity than another. This is just another way of saying that the first number is larger than the second. We can similarly define convergence towards negative infinity by saying that for every epsilon positive, there exists a real number capital X such that for every small x closer to minus infinity than capital X, the difference of f of x and L is less than epsilon. One advantage of thinking of small x as being closer to minus infinity rather than smaller than capital X is that sometimes this way of thinking helps you remember that the magnitude of small x is not small. It is in fact huge. One final remark. Here I assume the function is defined on all the real numbers. The same definitions can still apply if f is defined on a ray, meaning that if f is defined for all real numbers bigger than a fixed a, or all real numbers smaller than a fixed a. If f is defined on an interval from a to infinity, the notion of converging to L at positive infinity can still make sense. If L is defined on an interval from minus infinity to a, then the notion of converging to L at negative infinity can still make sense. Just to illustrate what convergence may look like, here I plotted some function on the real line, the horizontal axis being the input x and the vertical axis being the value of f of x. Going in the direction of positive infinity is going to the right. We said it appears that this function is convergent to some negative value. The amount of oscillation is getting smaller and smaller as you move to the right. So for any positive epsilon, you expect that once you go far enough to the right, all the remaining oscillation have amplitude less than, say, 1/2 epsilon. Of course, to actually conclude this, we have to be able to give a proof. A picture may be deceiving. For all I know, it may be the case that the oscillation ramp up in amplitude after it leaves the visible portion shown on my screen. Or maybe later on, there is a bunch of humps that show up for very large and positive x values. Similarly, it appears that going to the left we have convergence. Again, for any epsilon positive, it appears that the oscillations are getting smaller, and if we go far enough out, meaning very small x, meaning an x very large in magnitude but very negative, we should be able to conclude that all future oscillations have amplitude less than epsilon halves. Notice that the limits at plus and minus infinity need not be equal. The function here has a negative number as its limit at plus infinity, and a positive number as its limit at negative infinity. To reinforce our understanding, let's compare the notions between sequences and functions. On this slide, I show the definition of convergence of a sequence versus the definition of convergence of a real valued function at positive infinity. You see that the two statements are almost identical. The differences only having to do with the fact that for a sequence, the variable that we're using to say going far enough is the index n, which takes values in the natural numbers. Whereas for a function, the variable that we're using to say going far enough is the input x, which takes values in the real numbers. The fact that the sequence convergence concepts and the limits of functions at positive or negative infinity have such similar forms means that many of the concepts of convergences for sequences can also be carried over to limits of functions. Just to mention a few of them, first, we can analogously define the eventual upper bound and eventual lower bounds of a function in much the same way as we define it for sequences. All we need to do is again replace the measure of eventuality from the natural number index n of a sequence to the real number input x of a function. With these, we can define lim sup and lim inf of a function at infinity in the same way. Cauchy criterion for convergence can also be stated for limits of a function, simply by changing from a statement about the natural number indices n to the real number inputs. So it would say that a function satisfies the Cauchy criterion for convergence at positive infinity if for every epsilon positive there exists some capital X such that for any value x and y bigger than capital X, the difference f of x minus f of y is less than epsilon in absolute value. Statements that we have previously discussed about arithmetic of limits will still hold. So, when two functions both converge at infinity, we can add, subtract, multiply, and divide their limits as we are expected to be able to. In fact, we can consider the function limit as more general than the sequence limit. Here's a theorem. If a function converges to a limit L at infinity, then the corresponding sequence x sub n with xn equals f of n also converges to the same limit L. The short proof really just follows by noting that natural numbers are real numbers too. So first, the convergence of the function gives us the threshold capital X given an epsilon positive. To get the threshold capital N for the sequence, just take N to be some natural number bigger than X. This N exists due to the Archimedean property. Very importantly, the converse is, however, not true. That is, going to functions to sequences is a one-way street. We can give a counterexample here using the function f of x equals sine of pi x. For this function, we see that x sub n equaling f of n is 0 for all n, using that n is a natural number. And so the limit of this constant sequence is also 0. But the function does not converge to a limit at infinity. To prove this, we have to prove the negation of the definition of convergence. So we need to come up with an epsilon such that regardless of which capital X you take, there is a small x that is even bigger, such that the distance from f of x to the putative limit 0 is bigger than epsilon. For this example, we may take epsilon to be 1/2. Then, for any x, since there is a natural number n bigger than x, I can plug in x equals n and a half and find that f of n and a half minus 0 is equal to 1 in magnitude, showing that this difference is larger than the epsilon I chose. To connect the limit concept with something you are previously familiar with, the notion of limits at infinity is precisely the same as the notion of horizontal asymptotes. A function f has a horizontal asymptote y equals L if and only if either the function converges to L at positive infinity or that it converges to L at negative infinity, or both. Let's conclude this lecture by doing a hands-on example. We will try to find the limits of the function f of x equals x over root 1 plus x squared at plus and minus infinity. Here I will show you how to proceed for the case of plus infinity. The negative infinity case is very similar, but I do encourage you to write it out yourself in the same step-by-step format so you can make sure you understand how such a proof ought to be formatted. Our goal is to prove that the limit at plus infinity is equal to 1. Similar to what we did when we evaluated limits of sequences, we start by taking the difference between the function and the supposed limit. We find after rationalizing the numerator that the absolute value of f of x minus 1 is the same as the reciprocal of root 1 plus x squared times the absolute value of x plus root 1 plus x squared. Next, we limit to thinking about x positive. This is because we're trying to look at the limit at positive infinity, and so eventually we will have to look at only positive inputs. When x is positive, we find that the absolute value can be dropped, and the square root of 1 plus x squared is at least x. So we can simplify and say that the difference of f of x and 1 is no more than 1 over twice x squared. With the preliminary computation out of the way, we can now take a positive epsilon and choose our capital X. We will set x to be root 1 over twice epsilon. This choice is made so that 1 over 2x squared is equal to epsilon. And so we conclude that for any input greater than capital X, the difference between f of x and 1 is less than epsilon. And since epsilon is arbitrary, this shows that the function converges to 1. Again, I urge you to try writing out the correct version of the proof for the case of the input approaching minus infinity, just to get comfortable with the notions. Okay, that's it for today. See you next time.